So welcome everyone to the 46th episode of Covalent Academy. Today's episode is titled Under the Microscope, Your Electron Microscopy Questions Answered. So my name is Pralav and I oversee the Electron Microscopy and Failure Analysis group here at Covalent Metrology. But today's session is mostly geared towards taking your submitted questions and asking them to our electron microscopy and data analysis experts at Covalent. So our panelists of experts today includes the following. We have Dr. Yi Zhang, Kevin Wu, Esau Garza, Valerie Brogdon, and Dr. Ben Buford. I'll go into more detailed introductions in a minute. Also note that at the end of the session, we will be sharing both this recording as well as the slides on Covalent Academy, and I will provide instructions on how you can access them later. Okay, so before we dive into the Q&A, I just want to say a few words about our company, Covalent. So we are a next generation analytical services platform and physical lab headquartered in Sunnyvale, Silicon Valley. We provide both high quality data as well as actionable insights to help accelerate the research and development for our customers, especially those working in advanced materials as well as next generation devices. We have over 50 plus cloud connected instruments, several cutting edge analytical capabilities on those instruments, and we partner with several global leaders in characterization instrumentation. As you see, Ben, for example, works at Rigaku. That's one of our close partnerships. He works with us to develop very challenging data analysis applications. But we have other partnerships as well. In addition to the instrument manufacturers, we have over 500 qualified labs in our partner network. And through our offering called Covalent Connect, we serve as a one-stop shop where you can access basically any tool you can imagine in the whole metrology toolbox that's available as a service. So basically, in a nutshell, we perform comprehensive testing solutions and we provide several flexible business models to make it as seamless as possible for you to access these solutions. This slide gives you a brief overview of our most popular techniques and how we break them into categories. Right on the left, you see in green, that's the portion that I oversee. It's a lot of electron microscopy, SEM, FIB-SEM, TEM techniques, but also more in-depth consultation through our failure analysis team. So if you have yield issues, product failures, etc., our team is happy to sit down, consult with you, and help solve problems. On the right in blue is our other technical team overseen by Fuher Lee. That includes a whole host of techniques here to solve materials, chemicals, and surfaces type of problems. As you can see, we have a lot of different techniques ranging from optical characterization and microscopy to analytical chemistry like ICP, XPS, SIMS, etc. We also have a broad range of X-ray characterization tools like XRD, XRR. We're rapidly growing our mechanical testing capabilities, instron testing, as well as hybrid metrology on instrons and things like that. And finally, we have a whole suite of materials, property analysis tools like thermal analysis, surface area, zeta potential, etc. So just a reminder, you don't need to remember any of these techniques. There's a lot of different acronyms here. We will be sharing these slides so you can review them in more detail at your leisure later. All right. So with that, it's my pleasure now to introduce today's expert panelist. I'm going to start from the top to bottom here. So first we have Dr. Yi Zhang. He is the technical director of our electron microscopy group. He has over 15 years of experience in advanced scanning TEM or STEM imaging and spectroscopy. He got his PhD in material science and did his postdoctoral work at University of Michigan before joining Covalent. And thank you for being on the panel today, Yi. Next, we have Kevin Wu. He is a manager in our scanning electron microscopy or SEM team. He also has over 10 years of experience in the materials science field and specializes in SEM imaging as well as other analysis such as FIB-SEM, EDS or energy dispersive X-ray spectroscopy, as well as electron backscatter diffraction techniques. He has been supporting clients across a variety of industries, including semiconductors, batteries, and other advanced manufacturing customers. So thank you for joining us, Kevin. Next, we have Esau Garza. He's our operations director of our electron microscopy team. He's really helped develop our workflows and put us in a position to give you data, high quality data as fast as possible. But prior to Covalent, he's had a long career, 2+ decades in the material science field. He's been at WD working on hard drives, worked at Apple on display technology, and also at Intel working in depth on semiconductors. So we're very glad to have you on the panel today, Esau. Thank you. Our last two panelists, the first one is Valerie Brogdon. So Valerie plays a dual role here at Covalent. If you're a customer, you've probably interfaced with her during the technical quoting and scoping of jobs, but she also helps with marketing and outreach, technical marketing and outreach at Covalent. She has over 15 years of experience in metrology, characterization, and FA. Her core competency is in dual beams, especially PFib and gallium fibs. Prior to Covalent, she worked on multiple tools at an academic lab called CampCore, based out of University of Oregon. And she also worked at Thermo Fisher Scientific, helping develop a lot of fib automation routines. She holds several patents. She's a prolific writer and is published in this field a lot. So thank you for being on our panel today, Valerie. Finally, I want to introduce Dr. Ben Buford. So he currently is at Rigaku developing software and algorithms for X-ray metrology. But prior to that, he was also at Covalent and Intel working on similar types of challenging problems across different metrologies, including electron microscopy. So he received his PhD in electrical engineering at Oregon State University. And a lot of his algorithms are still being used and deployed at Covalent, and he continues to support us with any kind of advanced algorithmic development. So thank you for being here today, Ben. Okay. So now let's move on to the Q&A session. Just before we get into the Q&A, I just wanted to remind you, we're going to start with the pre-submitted questions that our registered participants have given us. But also note that you can submit questions as we go through a live Q&A tool. This can be found at the bottom of your Zoom screen. So please make sure to include your name with your question so that we tend to pick it for our panelists. So, okay, with that, let's start the Q&A. All right. So the way we're going to break down these questions, since we've received several and we're not going to be able to get to everything, but we are going to capture the main themes, and we're going to start with the more exciting and most relevant topics, including AI and automation first, then move into more advances in electron microscopy, followed by some of the latest developments in FIB and PFib, and finally into more practical troubleshooting for electron microscopy. So let's dive in. So the first question we have here is for our panelist, Ben. So Ben, this question is, how is AI and ML, so artificial intelligence and machine learning, being practically deployed today to automate electron microscopy imaging, defect detection, segmentation, and spectroscopy? Yeah, so please take the floor.
Great. And I prepared a slide for this, if you don't mind
Great. Yep.
going to that. That'd be great. So there's lots of different places AI can be used in this whole workflow. The first is to help with automatic or semi-automatic sample prep, where during that process, there's each tool vendor has their own method of using some sort of machine learning to help with alignment or judging sample quality. I'm not particularly an expert in that. I focus more on the data analysis side. So the rest of the points I've kind of highlighted here are more targeted towards data analysis. The first kind of quintessential place that neural networks or AI can be used is in segmentation or classification. And this works very well for large, complex EM data sets because there's a lot more information existing in these EDX or EEL spectra than you typically can analyze quickly and manually. So one example here I've shown in the top right is a paper that uses this to very quickly process all of the different EDX channels as well as the normal contrast imaging to quickly segment different types of materials. And any one of these channels you'd have a difficult time doing alone, but machine learning does a great job of looking at the bulk data or many channels at once and can pick out very different and distinct objects within it or materials within it. And really, this can't be done manually in a reasonable amount of time. You can this automation happens very quickly, and it doesn't even take that much training. There's various algorithms like principal component analysis that don't require any training, and you just throw it at it, and it identifies there's a lot of this material or a lot of this material, and can really speed up analysis. The challenge there is sometimes you have to, if you are using true machine learning with neural networks, you need to retrain it for each new type of application you have. So there's a significant setup cost, and it's really most applicable when either you just want to do blind analysis and have a person look at it afterwards, or you're doing the same thing over and over again, can address that initial development overhead. The next thing is then image denoising, where once you take your image, you do your fitting, however you're going to do, or look at your raw contrast image, and then apply denoising algorithms. And these are the same AI algorithms that have been developed for just like picture denoising or general optical microscopy denoising. It's not specific to the EM field, but can be applied to all of the same EM applications. And that really you can get this can help you get a lower dose if you collect for a small or faster throughput. We can collect for less time and then use AI to construct it back to something that's still human readable. The place I'm most interested then in is tomography reconstruction, which is both used in EM for various applications, as well as X-ray metrology, which is where I focus on it more. And the algorithms here that AI can help with are really the same across the board, regardless of your source of data. The tomography reconstructions, the theory behind it's pretty standard. And here the places AI can work is the first most, I think, impactful place is missing wedge reconstruction. When you're doing a tomography measurement, you can't measure directly in plane of the sample. You get too much absorption through the rest of the sample. So you're missing that information. But through an iterative approach, you can kind of reconstruct without that, and then use that end result to predict what that data would have been and run through the same reconstruction algorithm. And machine learning trained on that, you can train on one kind of generic data set and then use it on many other data sets, and it works pretty well. And I have a plot from another paper in the bottom right here that shows initially that missing wedge, you lose a lot of detail, but as you iterate over reconstructing and then regenerating the missing wedges, you can iterate a few times and get a much cleaner and more robust result that you wouldn't have been able to do without AI. Then also there's denoising, where you can denoise either the raw images you get initially, the sinograms, or the final reconstructed slices you're looking at, just to get prettier pictures. And then also there's ways to use automated sample alignment tracking, where you embed like a gold bead in your sample, and then either have the tool adjust to reposition that over time as you rotate to correct for any drift, or use that for alignment during the reconstruction process. And then finally, there's machine learning-based defect detection, which can be used for a variety of applications. The challenge there is that usually you need a kind of esoteric workflow for your specific application. So it's harder to have a one-size-fits-all defect detection. And it's really only more suited when you're going to be doing the same exact type of measurement many times. Yeah, those are the kind of best places that I've seen AI used, or machine learning used in EM automation and data analysis.
Thank you for that answer, Ben. I think it's very consistent with what we're seeing as well. Some of the repeatable on-tool tasks, right, for simpler lamella prep as well as on the back end for doing data analysis, as well as since we're a service lab, we create reports for customers. We fully embrace the use of AI to take care of those automated type analyses, but also sometimes more sophisticated things like reconstructing, denoising, and reconstructing higher fidelity data sets. So thank you for your perspective. Okay, so the next question we got was also for you, Ben. So you're the lucky one.
Great.
What are the most unexpected or transformative uses of AI in electron microscopy in recent years?
Yeah, I also have a slide for this. I think it might be the next one in the deck if you want to tab forward. I've kind of
Okay.
highlighted two places that I see this that I'm most excited about in the EM space. The first is this distiller application from the Lawrence Berkeley National Lab. And it's basically a framework that operates with the tool to automate collection and then uploading of that data to a cloud for large scale data analysis. And really, in machine learning applications, the place that I see the biggest challenges is just getting consistent, well labeled, repeatable data organized in a fine way. And that really limits pretty much every application I've worked on is getting the data in a way that we can quickly search, address it, and apply consistent machine learning algorithms to it, as well as the computational cost that comes with it. The tool computer is never powerful enough to analyze the many gigabytes of images that you get from that. So distiller is really exciting because I think it's going to pave the way towards, or at least this paradigm of working on things is going to pave the way towards scalable AI being more useful in the future. It really enables this big data collection and storage that we need for all future AI developments. As a more practical example of somewhere where we've seen good results with AI, it's in the cryo-ET or EM space, and I've included a paper down here to highlight that. And so traditionally when we do CT measurements or some various types of tomography measurements, you have to take a sample and tilt it back and forth a bit and take a series of images like in cryo-ET. And then you feed that into a normal image reconstruction algorithm to reconstruct it. But what people have been doing more recently in cryo-EM is taking hundreds of thousands of images of different portions or different samples, where if there's, in this case, these proteins or viruses that you're looking at, there's going to be millions of them in a petri dish. And just by taking kind of random images around that, you end up capturing a lot of what should be very identical samples rotated different amounts. And then with machine learning, they're able to predict, identify the same objects within that. So throw away anything that's not the sample of interest or that's a different shape. And then those objects will be randomly oriented within it, maybe with some preferred orientation, but more or less randomly oriented. And since they're all the same structure or same protein, you can use each one of those many images or many samples that you've imaged as a different rotated slice. And machine learning is great at automatically detecting them, automatically detecting what the rotation is, and then feeding that into the tomography reconstruction algorithm. And this lets us get many, many more slices than we would by just rotating a sample. And they've been able to construct down to like subatomic level reconstructions of these things, which is amazing to me. So places like that really let us take advantage of more data than we could manually align and use that and feed it into algorithms to reconstruct great things is really where I'm most excited about the AI space.
Oh, thank you so much for that answer, Ben, and thanks for sharing your perspective. Okay, so let's go to the next question here. So this one seems, since Ben, you spoke more about the data and analysis side, this one is more on the automation and AI being used on the tools themselves. So I'll divert this towards Esol and Valerie. Feel free to pitch in. But the question is, what parts of the whole end-to-end EM automation pipeline are still missing or hardest to implement in a high volume lab environment?
I can jump in on that one. Just because, during my time at Thermo Fisher, I spent several years sitting in a basement trying to automate the entire TEM prep process. And not to brag, but I am the first author on the patent. So I spent a lot of time trying to figure out how to automate TEM prep. And I would say the bottlenecks and the process are definitely where you get the manipulator to come in, pick up the sample, drop it off correctly, cut it free. Okay, that's actually quite hard. And the reason why is because the needle changes shape every time you use it. And it's really difficult to train an algorithm to recognize something that is consistently changing shape, right? It's the needle has a taper to it. Every time you weld something to it, there's a little blob of weld material. Every time you cut it free, it changes shape. So that's difficult. The other thing that is difficult is thinning. Often you need to endpoint on a very specific defect or a specific device in your sample. So it can be really difficult to train a machine to do that. And it's also difficult because every single material is going to respond to the beam differently. So that's something that's hard for machines to predict.
Awesome. No, thank you for that answer. Esau, would you like to add or
Sure. So
comment?
the one thing I can add is that even though we optimize recipes for thinning, there's no feedback currently in the recipe. So it's whatever you program it to do, it will just run its course. And as it's thinning, sometimes we develop polishing defects such as milling artifacts like waterfall, and the system cannot correct for those. But with the new version, especially with Temp 6, there's some machine learning going into there more and more, where I think we're going to get there, where there's going to be some active feedback going back into the recipe as it's doing the processing. So that will help to make it better and endpoint correctly or better.
Okay. So what I'm hearing is there's some difficulty with the needle attachment and dropping off the lamella on the grid. Also, end pointing is still an active area of development in the fib. To add to that, I also feel since we're looking at the whole pipeline, right? Anywhere you're transitioning between a tool, going from the fib to the TEM or vice versa, today, it's mostly manual, I would say. Of course, there's companies that have a lot of more funding than we do that can make bespoke robotic arms or different types of automation there to load samples. But that's definitely an area. There are solutions, they're just cost prohibitive, I would say. And then Sergey Kalinin's group at I believe University of Tennessee now has done a lot of work on how do you automate things within the TEM, right? Whether that's using STEM imaging or chemical information to drive to defects and things like that. So it's come a long way. There's also commercial versions like AutoSTEM and AutoTEM. Yi, do you want to talk a little bit about the TEM automation side, some challenges or what the current state is like?
Sure, I can add that few more. So I think the first issue, as you mentioned, I think the tool-to-tool connection is still the bottleneck. I said the fib and TM, they have their own automation workflow, and it's rather like isolated. So yeah, so the automated productivity between the fib and TAM, they're not matched. And also for the TM automation, what I've seen is that it's still pretty limited for the type of work, like some very repetitive sample work, and the analysis is very basic, like CD measurement, those kinds of things. So I think this is the area we can look forward to a more general AI model to solve this problem.
Yeah.
Yeah.
Basically, there's two types of high volume labs, right? There's labs with high repeatability of the types of samples. I think the current state of art can handle that. At a lab like Covalent, no two samples are the same. They're all different customers. It's way harder to deploy automation there and just say, go image this. No, uh, we need to understand what is the customer's need and make very bespoke custom solutions for them. So it's harder, but we believe the technology is coming and Covalent embraces all these innovations as they get better. I actually got a couple questions in the chat. Maybe let's pick one to switch it up. All right. This first one is a little bit more on the like practical consideration side for lamella prep. So maybe Esau and Valerie, what are some suggestions to minimize redeposition from the thinning process during inverted lamella prep? Esau, maybe you want to take it first? Or?
Sure. I think a lot of the times we get redep is the type of milling box you're using. Most folks tend to use the box milling as their thinning, but if you're getting a lot of redep, it's better to switch to a clean cut, and also increasing the Z of your cut, meaning that it's a longer uh, duration of the beam whilst you're cutting. A lot of redep is just because people are having a problem identifying where the true edge of the lamella is at that point. So also finding the right usually whether you have to use which detector is best for figuring out where you are actually at the lamella edge. So maybe switching from ice detector or to backscatter depending on the material that you're working with. I would say those are the main ways to minimize the redeposition.
Mm-hmm. Valerie, do
Yeah.
you want to add?
Yeah,
Go
definitely.
ahead.
I agree with everything Esau said. Definitely use the cleaning cross-section pattern rather than the box pattern. And make sure your fib is aligned. Like your beams need to be in good shape. You need to be able to see exactly where your lamella is. And don't extend the pattern too far over the edge of the lamella, because then what's going to be happening is you're going to be having ions hitting the grid, and then copper from the grid is going to be back sputtering onto the face of your lamella. And what you want to do is make sure your cleaning cross-section pattern is right on the edge of your lamella and nowhere else.
Yeah, some of this stuff is pretty tacit too, right? It's one thing to say do that, but observing it and being there with the operator is a great way to learn these type of things. It's a apprenticeship type dark art engineering fib, right? So one thing cool Covalent does that customers absolutely love is we provide live sessions where you can observe this process and ask questions and talk to the operator from your living room if you're not based in Sunnyvale, for example, or can't come in for any reason. So yeah, feel free to ask for live sessions and we can troubleshoot problems with you as we go.
And I had just one more tip that occurred to
Yes.
me. Make sure you're mounting the lamella in the proper place. There's people that mount the lamella on top of the grid tooth, and then there's another mounting style that's called the flagpole
Flagpole,
style.
yeah.
If you mount it on the edge, then you're not going to be hitting grid material when you mill down. So try to do the
Right.
flagpole style for this inverted prep.
There's many ways and it's very material dependent. You have to tweak the recipe, sometimes even the ions based on what you're working on. So yeah, come talk to us about it.
I think I
All
would
right.
also want to add
Yeah.
that was a good point from Valerie, especially when you mount on the V post. Most of the time you want to create a nice deep hole in the middle of the V so that there's room for the retip to go to and that's
Yeah.
come back to your sample. So
The material has to go somewhere. Give it
exactly.
space away from the sample to go into. All right. So let's move on to the one of the submitted questions. This one is for Yi. Yi, if you don't mind answering, what are the most useful applications of 4D STEM? Maybe even explain what 4D STEM is. Maybe not everybody knows. For battery or energy storage materials.
So for this time, let's say the traditional TM that detectors will collect like 2D like imaging information. So each pixel is but for this time, each pixel will collect both the imaging and the reciprocal like diffraction information. So we call that 2D real space and 2D reciprocal space. Uh, so so in my opinion, I think the phase and orientation mapping and the stream mapping are still two of the most widely used applications for this STEM today because these methods are already well established and the data processing uh, is much easier compared to the other for these STEM techniques. So for phase and orientation mapping will let us track the phase transformations and the different crystal orientations across the cathode material, for example, in the lithium ion phosphate battery. And the stream mapping will help will help us look at the local lattice distortions and strain distributions. Is also very useful for identifying where the failure may start. And there are also lots of studies they're using the differential phase contrast at DPC or center of mass images to directly visualize the lithium and oxygen, those kind of light elements, light atoms in the battery material. So compared to the conventional bright field image, DPC will provide a much higher signal to noise ratio at very low electron dose. So it's very good for the beam sensitive material. And also DPC can be used to detect like charge density variations, like accumulation at the electrode and the electrolyte interface. And also, there are some publications using for this DEM typography to reconstruct the phase images. So with that technique, we can directly get the projected potential map. And from this image, I think we call it a super resolution image, where we can see the distribution of the light elements or even the atomic scale displacement. So that's what I saw. Yeah.
Awesome. No, thank you for sharing the types of problems you're solving. At Covalent, we have what's called a precession system, PED, precession electron diffraction, which is very similar to 4D STEM, except for it gets rid of some of the dynamic scattering effects. You get cleaner diffraction patterns. But as you see, we do much more than just strain or orientation mapping, as Yi shared, for materials used in batteries.
We also have IDPC detector on Talos.
Yes, yes, we have both. Thank you, Yi. So this next question is also for you, Yi. It says, how do you reliably quantify localized chemistry using STEM EDS, considering factors such as probe size, thickness, sample thickness effects, and absorption?
Yeah. So I think lamella thickness is one of the most important factors for reliable STEM EDS quantification. If the lamella is too thick, then the spatial resolution will decrease because the electron beam will spread out as it interacts with the material. And at the same time, the X-ray absorption will increase significantly, especially for those light elements or low energy peaks. So at Covalent, we usually keep our lamella thickness around 30 to 80 nanometers to balance the spatial resolution and the signal strength. And once the lamella is prepared, we can measure its thickness using yields. And with the sample thickness, the density and the tilt, and we can apply absorption corrections, which is, I think, is critical for the accurate quantification. And another key step is calibrate the K factors. So using software, usually the EDS software will provide a default K factors, but using the default K factors is usually not enough because the detector efficiency, the geometry, they all will change the results. So at Covalent, we use either standard sample or IBS measurements to calibrate the K factor. So it will make sure that we will get the most reliable and accurate quantitative data. So in summary, let's say to get a reliable STEM EDS quantification, you will need a thin lamella, and we need to get the thickness number, and then we will do the absorption correction, and then properly calibrate the K factor.
Okay, no, thank you for that answer, Yi. So that's the one of the benefits of working with us, right? We have a Lamella prep team who understands these needs, the TEM team who can do all the collection and corrections, but also a data science team that can do the RBS or Rutherford backscattering correlation all in one seamless way. It basically seems to me like you need to know what you're doing if you need accurate data all the way from the prep to the collection to the analysis, and we've been doing this successfully for some customers. So yeah, let us know if that is important to you and you're not just looking at qualitative measurements, right? Uh, okay, so let's move on now to some of the plasma fib or PFib questions. These are Valerie, these are going to be in your ballpark. So the first one is seems like they're trying to understand when to choose what, right? So the question is, when is plasma fib preferred over a gallium fib? Uh, for example, for large area cross sections, porous materials, soft biological structures, etc. You're muted, Valerie.
Yes, now I'm unmuted.
Yes.
I actually included a couple slides on this. Let's see if they made it in. Can you click ahead?
With this one
Yeah. Oh, can you click ahead one more time? Do I have another slide?
here.
Okay, yeah. So the first part of answering this question is understanding the difference in the shapes between the two beams. So when you're using an LMIS source, a liquid metal ion source, usually with gallium, what happens is you have a cone-shaped emission. So you can choose bigger and bigger apertures that results in having bigger and bigger currents, but the size of your beam is going to increase exponentially with the size of your beam current. PFib, on the other hand, has a much more collimated beam. The emission is tighter and more collimated. So the spot size does not increase so dramatically with large currents. So now if we go back to the previous slide, I'll give you the takeaway here. So the result is that for very small currents, uh, the gallium fib is a lot better because it has a smaller spot size at smaller currents. But then when you use a large current, the P fib is a lot better because it has a smaller spot size at large currents. So when you're choosing between the two, it's really like if you need to make really precise fine cuts, like for example, the very last phases of TEM prep, that's going to be where you want to use a gallium fib. But if you have to make giant cuts and the bottleneck is volume removal and not necessarily really specific endpointing, then you're going to want to reach for a gallium or for a PFib. Did I answer the whole question?
I think so, yes.
Yeah.
Seems like PFib when you want to remove a lot of material,
Yep,
but gallium fib works really well
exactly.
for endpointing.
PFib is the workhorse for removing a lot of material really quick. Gallium fib is the workhorse for making fine little cuts like in
Yeah.
temp.
So yeah, traditionally one may think we have to do all of the prep in one tool, but that's not necessarily what you have to do in practice, right? You could also, for example, gallium can react, leave damage. You can clean that up with a argon mill or something like that. There's a lot of different things to play with here. Yes, for the sake of speed, it would be great if one tool could just do everything, but in reality or in practice, you have to use multiple tools to get the right prep quality for
Mhm.
your specific sample. So no, that answered the question. Thank you. Let's maybe jump a few questions ahead since we haven't gotten Kevin a question yet. So this is one of the more practical type of questions, Kevin. How do you balance high kV or high kilovolt slash high resolution imaging versus low kV surface sensitive imaging? What's your usual starting point for polymers or porous materials?
Gotcha. Okay. So the voltage regime for SCM is considered to be 30 kV and below. And so, in my opinion, high kV is sort of in the realm of 15 to 30 kV. Um, Based on physics, the shape of the beam is indeed sharper at higher kV, but at these higher voltages, the effective image resolution will tend to decrease. Because at higher kV, increasing the volume interaction of the beam. So you're getting more signal from further around your beam probe. And that beam broadening ends up reducing your image resolution. So you're going to be picking up more like subsurface features than if you had a lower kV beam, say around like 5 kV or less. In general, I would recommend for most materials to start at a lower beam energy, like 5 or 3 kV, because with the lower accelerating voltage, you have much lower beam interaction volume for surface sensitivity, and by extension, then your image resolution will also increase when you're trying to focus on the finer details of like nano-sized structures and whatnot. The additional benefit of using a lower kV beam is if you have a conductive coating applied to your sample for charging, then you will also reduce the amount of charging effects in your imaging, so that those charging effects won't interfere with kind of blurring edges and whatnot when you do that sort of thing. And this extends towards the second part of the question about polymers and porous materials. So high resolution imaging of polymers and porous materials will generally rely on mitigating the charging effects with a good conductive coating. So there are many ways to do that, but primarily sputter coating some sort of metallic material on the surface. And using a accelerating voltage of probably 3 kV or less is recommended for both polymers and porous materials. Because when you're looking at porous materials, you are probably looking at not only macroscopic pore features, but maybe nanoscale, submicron pore features that you would only be able to capture with a surface sensitive energy regime, such as 3 or 2 or 1 kV, that you would not be able to basically see with a higher kV beam.
Mm-hmm. No, thank you for that answer, Kevin. So it seems like everything else, it depends on the material, depends can you coat it or not. But in general, starting at a lower kilovolt to reduce damage and then slowly bumping it up as your material allows is the method you use to optimize the beam conditions. Okay, thank you for that. There's a question here about fib sample prep. So maybe Esau, you can take this one. How do you prepare challenging or beam sensitive materials for reliable TEM cross-sectioning?
So, yeah, beam sensitive materials are a little bit tricky, but the main thing is to minimize the total electron dose that you're applying to the sample. And this is throughout the whole process, from the SEM portion to the fib thinning and all the way to the TM imaging. And the way to litigate how much dosage you're putting on the region of interest is by constantly being aware that not to image on the region of interest unnecessarily. So having a sacrificial area maybe near your region of interest to do your beam focusing, you do stigmation, and you have to do this throughout the whole process, even during the TM imaging as well. And the other part is really understanding the materials that you're working with, meaning that you take the time to make sure you ground the sample correctly. If it needs spotter coating to litigate charging, you do that. And also if you need to mark your RI really well to minimize the time you're going to spend doing SEM, that also comes into play. And the last thing is really choosing the least amount of voltage and current throughout all these systems, meaning what is the minimum voltage and current you can use to be able to see the region of interest during the SEM, also during the fib milling, and also during the imaging. You can also do low dose TM imaging to prevent the total exposure. So yeah, that's basically it is. It's just limiting the electron dose throughout the whole process?
Mhm. No, that's a great question. I think I like that, Esau, because traditionally people focus a lot on what's the dose while thinning, right? But that's not it. You need to look at total dose through the whole process, prep the samples so that they're less amenable to getting radiolysis damage, maybe reduce the amount of exposure while thinning and prep, but then also in the TEM, be very careful about the beam conditions you're using to make sure the sample's not getting damaged or shrinking, is what I'm gathering. So, no, thank you for that. Okay, Valerie, this one's for you. So the question is, what are the limitations and best practices for plasma fib when preparing samples that have mixed mechanical properties? So I believe they're referring to something with hard, soft interfaces or um, practical materials.
Yeah.
Go ahead.
So this is a challenge, of course. So PFIB really shines on hard materials, right? Because you have access to much larger beam currents. But with mixed mechanical systems, you have to be a lot more intentional. So the reason why is because, of course, mixed materials are going to have different sputter rates. A softer material is going to sputter at a different rate than a harder material. And what that's going to result in is an artifact where you have, it's called a curtaining feature. It's a streak down the middle of your cut face where it milled a little bit faster or it milled a little bit slower. And especially if you're using high current, it's really going to amplify those curtaining artifacts at the interfaces between materials with different hardnesses or densities or porosities. Um, so one thing you can do is, of course, put a really thick cap layer on top. If the very first thing that the beam sees is something that's really rough and topographical, then the rest of your cut is going to be rough and topographical. But if the very first thing that the beam hits is something that's smooth and even, that'll help a lot. So sometimes I've even done up to 8 microns of tungsten deposition in my PFIB before I start a cut. You know, especially if it's a long cut. Sometimes I would get clients that would ask for a cut that's so huge, it's going to take me like 18 hours to make the cut. And it's just running like that. So the protective deposition has to last a long time. Like maybe sometimes you have to refresh the image, especially if you're doing continuous polishing over and over. And that deposition needs to be thick enough to survive multiple beam imaging refresh attempts. The other thing you can do is there's all kinds of techniques to mitigate curtaining. One thing that's really popular is a rocking mill technique. So what you do is you have your cut face like this, right? But if you rotate and then tilt the stage, the beam will come in like this. So the beam will be coming in kind of diagonal to these artifacts on your stage that are causing the curtaining. Okay, so now your curtains are going this way. But then you can do the exact opposite rotation and tilt, and your curtains will go this way. So essentially what's happening is you're creating curtains going diagonally this direction, and then you're creating another set of curtains going diagonally this direction, but it polishes off that first set because it's the opposite direction of curtaining. And sometimes that works really well. I find that it works really well on geological samples. Sometimes it does not work really well. You know, just like Prahlav said, fib is really a dark art. So it's all about just trying things until something works. But I will add probably the most obvious thing you can do is step down your current a lot. Once you approach the final polishing, you need to be doing that with a very low beam current. Also, a lot of people have access to PFIBs that have different ion species. Xenon is obviously the most popular, but more and more we're seeing ion species like oxygen and argon in the tool. So when you're using argon, you can kind of think of it as like chipping away with smaller ions. So it's kind of a sandblasting technique rather than just throwing baseballs at your sample. So it'll have a slower removal rate, but it'll be a little bit cleaner of a substrate. And then I'll add this one last point. If you happen to be cutting through an organic substrate containing carbon, you can use an oxygen beam, and that works great for removing artifacts in organic substrates and biological substrates, because what happens is the oxygen combines with the carbon in your substrate. And so you have a chemical removal mechanism in addition to just the mechanical sputtering of the beam. And that results in a really clean, nice looking cut face on organic substrates. So that's my advice for your question.
Oh, no, I really like that. So there's a mix of prep related tricks you can play, but also understanding the interaction between the beam and the sample, and whether it's a mechanical sputtering or chemical removal, those type of details can help reduce curtaining a lot. So it is possible. Just need to speak with Valerie and Esau about those things. All right. So this next question is on SEM troubleshooting. So Kevin, I'll give this to you. What is your preferred coating strategy? So putting a metal or conductive coating on the surface for non-conductive samples if you're trying to achieve high resolution imaging, EDS analysis, and what do you do in the case of beam sensitive materials?
Great question. So sample conductivity is very important to avoid charging, improve imaging quality, avoid beat damage, etc. for non-conductive materials. So when high resolution imaging is the greatest important, the general strategy is to deposit a conductive coating that is as thin and fine-grained as possible, depending on your sputter coating tool setup. So for most general sputter coating tool setups, platinum is the kind of standard material for fine-grained sample prep. But there are other materials such as chromium and iridium that can deposit even finer grained coatings on your samples. Those tool setups do require a much higher vacuum when you're depositing these materials, like a turbomolecular pump. So depending on your actual tool setup, platinum works well for most things. If you can afford to go a little higher, then you should think about either choosing chromium or iridium for your sputter coating material. So for EDS, it becomes a understanding what material can you deposit that would not confuse or interfere with the EDS spectrum analysis. And so when you deposit a sputter coating material on the surface, it will also generate its own X-rays that you will detect in EDS. And you may or may not know that X-rays from different elements can overlap with each other. For example, platinum and phosphorus overlap quite closely together, and then gold and sulfur also overlap quite closely together in the EDS spectrum. So if you anticipate that your area of interest has neither sulfur or phosphorus in it, then you could use either gold or platinum to sputter coat your sample and not have to worry about those sort of overlaps. But if you're not quite sure, then the recommended sputter coating material would be carbon. So with carbon, it's such a low energy for the X-ray peak that it will not overlap with any other, say, metals or other elements. But it also has a much lower X-ray absorption or reflorescence compared to the others. So your X-ray EDS data will be a lot cleaner. For beam sensitive samples, it's important to note that you want the sputter coating parameters to be as low energy as possible during the actual sputter coating process so that you don't accidentally harm your beam sensitive sample during the sputter coating process. So it's generally recommended to keep your plasma power pretty low, like below 20 watts with a very low current, so like below 20 milliamps or so, and to sputter coat your sample with short bursts, say like 10 seconds per cycle, so that you don't accidentally overheat your sample during that sputter coating process. And then moving forward, when you actually image your sample, you also want to keep your electron beam dose very low. So very low beam currents and accelerating voltages, so below 3 kV or so, and maybe 50 picoamps or less. And do frame averaging as well, which will reduce the dwell time of the electron beam on your sample.
Oh, thank you for that answer, Kevin. What I'm gathering is you have to be super thoughtful and every step matters, right? It's not just SEM or just deposition. You have to be thoughtful not only in the choice of the materials, but the conditions with which you deposit them so that they're not damaging your samples. The grain size is appropriate so it doesn't obscure features. The thickness is correct. And then what you do in the SEM itself in terms of optimizing conditions. So the
Pro-
answer is not always put thick gold palladium, which is what happens a lot.
So,
Isam,
Pralab,
you wanted to add to that?
yes, yeah. I wanted to add also
Go
if
ahead.
something to consider when you're choosing a sputter material, also consider whether or not you're gonna follow up with fib or lamella prep. Especially with platinum, the grains are big enough that they'll cause an issue if you're going for a small RI. So that also has to be considered. What is the next step you're gonna do in the analysis?
Yes. Thank you. Okay, maybe we'll do another quick Q&A that just came up. The question is, what AI/ML tools are you using for image analysis? And this can be anyone on the panel. If you don't mind sharing some popular or very useful ones.
Yeah, I'll start with this, and other people please chime in with what you use as well. So for the most part, these more bespoke image processing algorithms that we need to kind of fine tune for each component, we end up using open source software for it. I don't have a slide for this, so good luck, Pralaf. Yeah. We usually use HyperSpy to just import the data into Python, and then traditional machine learning things like TensorFlow or Keras or other things to do any real machine learning things. You can also just use ImageJ, has a bunch of built-in AI machine learning things, as well as I think Zeiss has a toolkit, and there's a couple other companies that will have things to do the basic analysis. Yeah, but I'm curious on the Covalent team if there's anything anybody else uses regularly for this.
Yeah.
I've used
Yeah.
Aviso a lot, which is a software that's available from Thermo Fisher. I use it for a lot of 3D, especially because there's a lot of great applications for slice and do on PFib. So when I do a large area slice and do, I have this big stack of images, and I use Aviso to auto align them. And there's all kinds of interesting filtering applications to remove noise, all kinds of automated segmentation tools.
Awesome. Thank you,
Yeah.
Valerie. Kevin and Esau, any favorite AI machine learning tools?
As Ben already mentioned, the HyperSpy. That's the
Yeah.
one.
Yeah.
Yeah,
I
that's the
think
one we use
ImageJ
more.
and Veka are also quite underrated. They have a lot of open source tools out there too that can do quite a bit with a little bit of programming. And you can now use AI to write the scripts for you, which is also great. You can get to some sort of segmentation or deep learning type applications relatively quickly now.
Yeah. Especially for something you need just quick and dirty for maybe a couple samples, not a production
Yes,
ready workflow.
which
ImageJ
is which
really
is
can
the
do
world
a
we
lot.
live in.
Yeah. Yeah.
Kevin or Esau, any last ones? We only have a minute to go, so.
No, I was just gonna pair what Valerie said. I've also used Aviso for slice and view segmentation for similar types of
3D
projects.
tomography.
Yes, 3D
Okay.
tomography.
I think for us, the space that we're kind of exploring more is more for recipe development for auto temp 6. That's where we see the most value, where we are also using machine learning to improve the recipes. And there's some AI component that we're starting to integrate.
This is, for those unaware, this is Thermo's latest lamella prep automation, Auto T M6, which we have at Covalent. All right. So with that, I want to thank all our panelists, Esau, Valerie, Yi, Ben, Kevin, for your time. Thank you so much for sharing your perspectives and answering our customer questions. I hope this presentation gave you all a sense of how much really we can do with electron microscopy, right? And if you need help, always feel free to reach out to us. We'd be happy to chat with you. Let me share my screen again. Share so you can see this. Okay. Um, just now in the link, I believe Sophia, in the chat, Sophia put a link there, meetings.hubspots.com/covalent metrology/project discovery. You can reach us and talk to our experts at that link. Also, as you saw, our EM team here shared a lot of great information. If you want to go back and review these slides, as well as many of the other great topics that Covalent has covered in the past, you can find them at academy.covalentmetrology.com. With that, since it's exactly 12 p.m., it's time to wrap up. Thank you all for joining today. And yeah, please stay in touch. Let us know if you need anything. Have a wonderful day. Bye.